Okay, so in a previous video, what we looked at is we looked at parametric surfaces, right? Okay, and the two parametric surfaces that we considered in previous lecture was truncated plane, right? This truncated plane over here. And then the next one that we considered was a cylinder, right? So a cylinder that's centered around your z-axis with finite height, right? Okay, so the cylinder was lying between your plane z is equal to 0 and z is equal to 3. So it had a height of 3 over here, right? Okay, and as I said, it's centered around your z-axis. So both of these were examples of parametric surfaces, and how you specify a parametric surface is, well, most of the time we're going to be using this vector notation here. Right, so you specify a parametric surface and you're going to be using two parameters u and v here, right? So your parametric, this vector form of your parametric surface, what you're doing is you're specifying x component, y component, and z component, right? And the u and v need to lie in a region R, right? Okay, so parametric surface would give you some surface that's floating around in three-dimensional space like this, right? And now what we want to do is we want to do a surface integral on a surface, parametric surface like this over here, right? So either say something like this, which is flat, right? Or a parametric surface, we want to do a surface integral over something that's possibly, well, that's curved like this over here, right? Alright, okay, so how are we gonna define our surface integral? Well, this is the definition here, right? So notice what you're going to do is you're going to use the information from the parametric surface, right, to actually calculate your surface integral, right? So what your method for evaluating your surface integral should really remind you of what we had the definition of a line integral, right? How you calculate a line integral, right? So if you look over here for what we did for line integrals, right? What we're doing for a line integral is we are integrating, say, a vector field over a parametric curve, right? And now what we're doing is we're integrating, well, first of all, a function over a parametric surface, right? Okay, now how did we work it out for a line integral, right? What we did is we used the information, right, that was given in the parametric surface, right? So for example, over here, if I wanted to integrate this vector field, what I use is I use the information, this is the x over here. So I put the x, which is equal to 1 plus t, into my vector field, right? So I put the x, which is 1 plus t, into the vector field, right? And notice when I put the x is equal to 1 plus t, I got 1 plus t squared I, right? Which is this over here, right? Okay, so when we did a line integral, what we did is we used the information from the parametric surface to actually calculate the line integral, right? And likewise over here, what we're going to do is we're going to use the information from the parametric surface now to calculate the surface integral, right? So you're going to take your information, so this x, the x component, which would be a function of u and v, would be given to you. Likewise, this y component will be given to you, this z component would be given to you. And you're going to take that information and you're going to put it in over here, right? And that would be, well, your starting point as to how you're going to work out your surface integral, right? Alright, so before I actually get into the calculation of the surface integral, right, let me see if I can give you an interpretation of what your surface integral would mean, right? And in order to do that, I'm going to review some basic stuff from physics. Right. Right. Okay, so let's just remember what density is, right? So I have, for example, I have a metal cube that is of side length 2, right? Okay, so for example, well, this is your metal cube here, right? This is of side length 2. By side length 2, I mean each of your sides over here of the cube is of length 2, right? All right, now, well, what's the volume of this cube, right? Well, the volume of this cube is you're gonna take it's gonna be side by side by side, right? So when you multiply your two sides over here, what you're gonna get is the area of if you want the bottom, and then you multiply by the height also. So you're gonna get 2 times 2 times 2, right? So the volume of this cubed is 8, right? 2 times 2 cubed is 8, right? All right, so this is a cube over here, and I'm saying that this is a metal cube, and if this metal cube it actually has for the sake of this example, it will have density 3, right? I'm not considering the units over here, right? Okay, so it has density 3, right? So what would be the mass of this metal cube, right? If the volume is 3 and it has a constant density, right? So that what that means is that throughout the cube, right, at each point in the cube, your density is always equal to 3, right? Okay, so what would be your mass in this case, right? Well, the mass is just simply density times volume, right? Right, and the density I said is 3, right? And the volume of the cube is 2 cubed, which is 8, right? Okay, so the mass over here is just density times volume, which is 3 times 8, which is 24, right? Right. Okay, one thing you want to notice is that if your density happened to be equal to 1, right, then what you'd get is that the mass would be equal to 1 times the volume, so the mass would be equal to the volume, right? Okay, but in this case, the density is 3, so the mass is 3 times the volume, so 3 times 8, which is 24, right? So, for a different example and probably closer to what we want, right? Let's now consider instead of having we had a cube in the previous example, a metal cube. Now what we have is a metal plate, right? Okay, so this metal plate, it's a square metal plate, and the side length is 2, right? And I can look at this metal plate in two ways, right? Either I can think of it as having 0 thickness, right? Or having if the thickness is uniform throughout the plate, right? As you go from point to point, it has some thickness, right? And the thickness is uniform, right? But let's, for simplicity over here, I'm just going to regard this as some sort of ideal metal plate where it has 0 thickness, right? Now, this is a metal plate over here, right? Well, the metal plate is going to have weight, right? So the weight of the metal plate, the mass of the metal plate is going to depend on the density of the metal, right? So in this particular example, the density over here is 5, right? But you want to notice that this is a different concept of density from what I had for the cube, right? Because now what I'm looking at is areas over here. So a certain area, at a certain point, you're going to have an area density, right? So the notion of density we want to use for a flat surface like this over here, for a surface, a two-dimensional surface, is going to be area density, right? Okay, so this metal plate in this example will have an area density of 5 for this example. And to get the mass of the metal plate, well, the mass of the metal plate would be the total area, right? And what's the total area here? The side length here is 2, right? So the area of this square metal plate is 2 by 2, which is 4, right? Okay, so the area is 4, right? And so the mass of this metal plate would be area density, right, which is I'm saying is 5, right, times the area, right? So area density times area density is 5, right? Area is 4, right? So the mass of this metal plate would be 20, right? Okay, so what I really want you to get out of this example is if I have surfaces like this, I can have I have the concept of area density, right, which is analogous to just normal density. But where you use area density is when you're looking at surfaces, right? And you imagining these surfaces have 0 thickness, but they're still gonna have some mass, right? And the mass would depend on the density of the surface from point to point, and that density is an area density, right? All right. So density in the normal sense, and this you should have seen in your physics sense, so is normally it could be denoted as rho, right? And area density, right? We're going to use rho subscript capital A to indicate area density, right? All right, and Similar to the example that I did over here, right? Is if my area density happens to be equal to 1, right? Then when I work out the mass, it'll be mass times area density. Mass is equal to area density times area, right? And if the area density is just equal to 1, then the mass is equal to the area, right? So the mass is equal to the surface area when area density is equal to 1, okay? Okay, so now what I want is if I have a surface, right, but the surface isn't necessarily, say, flat like this in a plane, right? The surface is living in three-dimensional space, like this green surface over here, right? What I want to do is I want to get the mass of it, right? Okay, so this surface S over here, which is living in three-dimensional space, right? What I want to do is I want to get the mass of it, right? And I'm saying from point to point, it has an area density, right? Now, if the area density was in fact constant, right, I could really just use the same formula that I have from over here, right? All I'd need to do is figure out what the area of this surface is. It isn't necessarily that simple to figure out what the area of this surface is, right? But in this case, it's not bad because the surface is just a truncated plane, right? And the area of this surface, this is it's going to be, it's a square, right, with side length 1 and side length 1. So the area of this surface, even though it looks sort of slanted over here, right, if you want, you could think of this as, say, like a face of a cube or side of a building or something like that, and the area of this side over here is 1, right? Okay, so the area of the side over here of the area of this surface over here is in fact equal to 1. And if I had, say, a constant area density, right, so for example like 5, right, then the mass is going to be 5 times the area, which is 5, right? Okay, but what can happen is now it's possible that the area density, so from the density from point to point, right, could change, right? So for example, is we're thinking of this as, say, like a metal plate, and if you have some sort of like manufacturing imperfections or something like that, the density could potentially change from point to point, right? Okay, so if your density, the area density is changing from point to point, right? I can still actually still work out what the mass of this surface is over here, right? In a sense, what you're going to be doing is just area density times area, but it needs to be a little more sophisticated than that, right? Okay, so for example, over here, the area density could be lower than over here where the area density is higher, right? So you want to be able to deal with that, right? And how you deal with that is you use a surface integral to work out the mass of okay, so if I want to get the mass of this metal plate where the area density is variable, right, then what I would do is I'd use a surface integral, right? Okay, so what do I mean by variable area density, right? Let's consider this function over here, right? So this function is rho right, rho of the area density function is, it's a function of x, y, and z, right? Which means at different points in three-dimensional space, right, I'm going to get a certain value, right? Okay, and this particular function is relatively simple. It just depends on z over here, right? Okay, so when the z is equal to 0, which is down here, so in particular on this bottom edge over here, this is where z is equal to 0, right? So on this bottom edge over here where z is equal to 0, your area density is going to be 1 plus 2 times 0, which is just 1, right? So on this bottom edge over here, the area density is 1, right? Okay, and over here, right, this is where on this top edge over there, that's where z is equal to 1, right? So if you want, I can project this onto the xz plane, right? And you see in that your top edge over here, that is where z is equal to 1, right? Okay, so on this top edge, z is equal to 1, which means that on this top edge, according to this area density function, right, the area density is going to be 1 plus 2 times 1, which is 3, right? Okay, so on your bottom edge over here, according to this area density function, the area density is equal to 1, and on this top edge over here, the area density is equal to 3, right? And this is a linear function, right, which means that you're going to have a linear change in your area density from 1 over here to 3 over here, and that area density is going to change linearly with height, right? So in particular, in the middle over here, when the z is equal to a half, right, what you're going to get is an area density of 2, right? So area density of 1 on the bottom edge, area density of 2 in the middle, and area density of 3 on the top, right? So the area density is increasing as you're going along, right? Right, and what I want to do is I want to get the mass of something like this, right? So again, you just really think of this as, you're just thinking of this as some metal plate over here, right? And the density of the metal plate is in fact changing, and I want to figure out what the mass of it is, right? And that is what the surface integral of a function will do for me, right? It'll calculate the mass of this, right? Let's see if we could actually work it out without doing the using a surface integral first, right? Okay, so right, so I said that your bottom edge over here, the area density is equal to 1, right? Your top edge over here, the area density is equal to 3, right? And what you have is you have a linear, because this function here is linear, right? It's linear in z, right? What you're going to have is you're going to have a linear increase from 1 over here to 3 over here, right? Which means that you can talk about your average area density for this this surface over here, right? This metal plate, right? So the average area density is between the 1 and the 3, which is actually 2, right? So average area density is, you can take values at the bottom edge, values at the top edge, right? And just take the average of those, 1 plus 3, which is 4 divided by 2, right? Okay, so 4 divided by 2 is 2, right? So the mass of this, because this function is relatively nice, right? The mass of this, even though that the area density is changing as you go from this bottom edge to this top edge, right? The mass of this, you could actually work this out without using a surface integral. The mass of this would be the average area density, which is 2, right? Times the area of this, and the area of this, we talked about this. This is just a square of side length 1, right? Okay, so the area of the square is 1, right? So the mass of this would be 2 times 1, which is 2, right? Okay, right. Alright, so this is, so just to give you an idea of where we're going to use the surface integral of a function, right? Right, and over here, so what I'm saying, right, is to calculate the mass of S, which is the same calculation that I had up here, right? That the mass of S turned out to be equal to 2, right? The more general way to do it, right, would be to use a surface integral, right? So you use a surface integral of your area density, right? Okay, and the area density we saw was, in this particular case, was varying between 1 and 3, right? And the area density was specified by this function 1 plus 2z, right? Right, so to get the mass of this surface S over here, what you're going to do is you're going to integrate your area density function, right? Which is a function, if you want, on this surface S over here, which is giving you different values on your surface S here, right? Okay, so for example, down here on the surface S, the value would be 1 on the bottom, and it would be 3 on the top, right? So this function over here is describing values on the surface itself, right? And what you're going to do is you're going to integrate that function along over this green surface here, right? Okay, and when you integrate that function over that this green surface S over here, what you're doing is, if you want little small pieces, you're looking at the area density, right? Times the area for this small part, and then you keep adding that up, right? And overall, what that will give you is that will give you the mass of this this surface that we can regard as a metal plate, right? So the mass of this metal plate, right, when the area density is potentially changing. Okay, so that's our interpretation of surface integral of a function, right? So this is an example of a surface integral of a function. You have your function over here, and what you're integrating is you're integrating over some surface S here, some surface S that's floating around in three-dimensional space. Okay, so the notation is for a surface integral is you're integrating a function, right, over a surface S, right? And the notation, this ds over here is to indicate that you're using a surface integral, right? This is going to be a surface integral, right? Right, so this function f(x,y,z), right, is, so when you're looking at a surface integral, right, how you want to conceptualize it. Okay, so you have, if you're going to work out a surface integral, right, you're going to have two things, right? You're going to have a function, and you're going to have some surface S, right? Now that surface S is some surface that's in three-dimensional space, right? That's floating around in three-dimensional space, such as this square over here or the cylinder that I talked about earlier, right? Okay, so for a surface integral, I'm going to have some surface S over here, and I have some function defined on that surface, right? So at each point on the surface, I'm going to have certain values, right? And in the case of when I was talking about the area density, right, the values down here were 1, the values over here were 3, right? The values in the middle were 2, right? And what we want to do is we want to integrate those function values over this surface S over here, right? All right, and okay, so that's interpretation of surface integral of S, right? And now what we want to see is we want to see how to actually calculate it. Before I get into the calculation of the surface integral, right, let's just recall one last thing here, right? If remember what I said over here, right? So for example, if I have the square metal plate, right, that is just happens to be on the plane, right? Then, and if this has an area density that is actually equal to 1, right? Then the mass of it, when I work out the mass, right, I'm going to get the area density which is equal to 1 times area, so that the mass is just equal to the surface area, right? Right, okay, so now in this case, right, if I have now the surface that's living in three-dimensional space, this parametric surface, right? And if the area density now is just equal to 1, right? Okay, so if your area density is just equal to 1, right? Then when you do a surface integral with an area density just equal to 1, right? You're going to get something analogous to what we just had, right? So if I do a surface integral, right, where my area density at each point is just equal to 1, then all you're doing is you're just working out the surface area of your parametric surface S over here, right? So this is something that we're going to use, right? And it's something that you should know, right? So if you're doing a surface integral, right, where your function inside there is equal to 1, right? So if you're doing a surface integral where you're just integrating 1 over your surface S here, right, then what you're doing is you're calculating the surface area of S, right? So this definition 1.80 will tell us how to calculate your surface integral, right? Alright, so I have some parametric surface, right, that is given to me, right? Or if you don't, if you're just given the surface, somehow you would need to know what the parametric surface is, right? There's one exception to this case that we will get to, right? But usually what you're going to have is your surface S is a parametric surface, right? Okay, so for example, this cylinder over here, right? So this is a cylinder lying between your plane this is a cylinder lying between the plane Z is equal to 0 and Z is equal to 2. So this cylinder over here, and this cylinder actually has radius 3, right? Okay, so this is a parametric surface, right? Notice the parameters in this case are called theta and z, right? Here the parameters are called u and v, right? But it doesn't make a difference what you call the parameters, right? Okay, so here your parameters are theta and z, right? this is a parametric description, and then the parameter values need to lie in R, right? And this R over here is a rectangular region, right? So we talked about this when we looked at parametric surfaces, right? Okay, so if I have a parametric surface such as this over here, right? What I'm going to do is, in order to work out my surface integral, right? So the surface integral is of this form. You have a function of your three variables x, y, and z, right? And you're integrating it over the surface S, right? Which is this surface. An example is the surface S over here, right? So you're integrating it on the surface of the cylinder, right? Not the interior, and so, right? Just the outside of the cylinder, right? Okay, so to work out this sort of surface integral, what you're doing is you're using your parametric description, right? So wherever you see the x over here, you're going to replace by this component function, right? The component function for the I. Where you see the y over here, you're going to replace by the component function for the j. Where you see the z, you're going to replace by the component function for the k over here, right? Okay, so this x over here, you're going to replace by component function. Y, you're going to replace by component function for the j. This z, you're going to replace by the component function, right? You're going to have this term which is Ru cross Rv, and you're going to be taking the modulus of that, right? So you're going to take the length of it as a vector, right? And we saw examples of what Ru cross Rv is already, right? Okay, so for this cylinder here, where you had, this is your parametric description, we worked out R theta, right? Okay, and we worked out Rz, right? And what you need to do is you need to take the cross product of the R theta and the Rz, right? If you had a problem with a cylinder, right? Okay, so this sort of object over here with Ru cross Rv, in fact, we saw already, right? We talked about in the lecture with parametric surfaces, right? Okay, and we did an example here where we had R theta cross Rz, right? This is slightly different over here. What I'm doing is calculating R theta Rz for specific vectors, right? Over here, this would be more general, right? So you'd see that, right? But the main point is that we have this object Ru cross Rv, right? The Ru you're getting by differentiating your component functions here, each of these with respect to u, right? The Rv you're going to differentiate each of your component functions here with respect to v. You're going to take the cross product of that and then take the magnitude of the resultant vector that you get, right? So that is what this Ru cross Rv is over here. And then notice what this is this is an integral over R over here, right? So it's an integral over your parameter space, right? Remember, for a parametric surface, what you have is you have a parameter space for your region, right? Okay, so the big R over here, an example of the big R, it would be this pinkish rectangle over here, right? Okay, and an example of the corresponding parametric surface would be this green cylinder over here, right? Okay, so this is the R and this is the S, right? And when you take different UV points in R, right, what you get is you're going to get a corresponding point in the surface S, right? So you see in that when I take different parameter values UV, right, you see that I'm going to get different points. Okay, so when I take different parameter values, which are pairs of UV, right, I get different points on the surface S, right? Okay, so this is your R over here, and this is the S over here for your parametric surface, right? Now, when you're doing your surface integral here, what you're doing is you're integrating a function of three variables over a surface S, right? So you're integrating a function over this green surface S, right? So in terms of the area density and so on, right, what you're thinking is that at each point on this surface S over here, you have a certain function value, right? You could interpret that function value as area density, or you could just interpret it as just some function value, right? But the point is, this f of x, y, z over here, what that means is that on each point on your surface S here, you're going to have a certain function value, right? And what you're doing is you're integrating those function values over that surface S, right? And how you're actually doing that, right? So this is your surface integral. The surface integral is the integral of your function values over this, for example, this green cylinder S over here. But how you're going to work it out is you're actually pulling back all your information onto this region R over here, right? Okay, and while over here it's complicated, right? What you're trying to do is integrate over something that's curved, right? How you actually work it out is you pull back the integral over something that's flat over here, right? And once it's flat like this, right? Okay, so once it's flat like this, so this is your R over here and this is your S over here. So here, what you're doing is the surface integral is over S. So this is an example. This green guy is an example of S. And to work out the surface integral over S, you actually work it out as a double integral over this region R, right? Now this region R is in the plane, right? So you take your information about the function and so on, you pull it back over this region R over here, and here you work it out over this region R, right? So what you're doing is all of this over here is just some function, right? Right, that we integrating over R, right? And we saw how to do that already, right? So this is just some function over here, right? And well, the plane is UV, right? But that's just really just it's the same idea as integrating over the XY plane, right? Okay, so you have just some function over here, right? And what you're doing is you're integrating that function over a region in the plane, right? And this sort of integral of a function over a region in the plane is really just a double integral, right? So the idea is that if you have your surface integral here, what this definition is doing for you is converting your surface integral here, right, into a double integral. It's converting your surface integral, which is an integral over this green surface S over here. It's converting it to a double integral over a region in the plane, right? And the idea is this is more complicated, right? So you reduce something that is complicated to something that we know how to do already, which is a double integral. Right, so let's work out this example here. We have this function, right? And we want to do a surface integral of this function, x squared y plus z squared, right? Over your surface S, right? And you're given what the surface S is over here. That the surface S is part of a cylinder, right? So this x squared plus y squared is equal to 9, right? And you want to remember, we saw what this was when we did our lecture on parametric surfaces. This is a cylinder centered around your z-axis of radius 3. And this actually has infinite height, right? But they're saying that this cylinder, what you're going to do is you cut it so that it lies between these two horizontal planes, z is equal to 0 and z is equal to 2, right? So it's going to lie between the two planes, z is equal to 0 and z is equal to 2, right? So the actual surface is the surface of the cylinder over here, right? It's not the planes, right? It's just this surface S over here, right? Right, so if you want a next picture of what the S is going to look like, right? It's a cylinder centered around your z-axis, so it's this green surface S over here, right? And this S, well, over here it's not given parametrically, right? It's just given saying that it's a cylinder, right, of radius 3, right? So there should be a 3 here. Right, so it's a cylinder of radius 3, right, that has height going between z is equal to 0 and z is equal to 2, right? So you're seeing that the height of the cylinder is between z is equal to 0 and z is equal to 2, right? Right, but it's not given to you parametrically, right? And this surface integral here, to work out the surface integral, you would need a parametric description of your cylinder, right? Okay, so first thing we need to do is come up with a parametric description, right? Right, now your parametric description of a cylinder, right? This is standard, right, for a cylinder centered around your z-axis, right? So to get a cylinder centered around your z-axis, it's going to be of the form cos theta I sine theta j plus zk, right? The parameters that you're going to use would be theta and z, right? What the theta is the theta has a meaning, right, where the theta is actually measuring angle for you relative to the x-axis, right? So as you go from here to the y-axis and you move along this circle, right, this bottom circle over here, your theta is going from 0 over here to pi on 2, right? And then when you go around to this point over here, you'll go to pi, right? When you come along a circle over here to here, you come to 3 pi on 2, and then finally you come back around, it's 2 pi, right? So the theta is actually measuring angle as you go around the cylinder, right, in a radial fashion, right? And the z in the parametric description is actually referring to height, right? So the z is actually just the normal z that you see from your in your coordinate axis, right? Okay, so I have any cylinder centered around my z-axis, right? I can write cos theta I, sin theta j. The values in front here, right? The 3 and the 3 over here is the radius of the cylinder, right? And here, because I have 9, which is 3 squared, right? The radius of the cylinder is 3, right? And your parameter values here, the theta going between 0 and 2 pi, right? Means that you're going straight around the cylinder, right? Okay, so if your parameter values, so this is your parameter values, this is your region R over here, right? So this R over here is this pinkish region over here, right? Okay, and here the theta, I'm using, they call in the parameters U and V, right? But for purposes of this notation here, right? The U is theta and then the V is Z, right? Okay, so if I didn't have 0 to 2 pi, right, and if I had, say, for example, from 0 to pi, right, what I would have is I would have just, say, half of the cylinder, right? So in order to get the full cylinder to go straight around, right, I need to use 0 to 2 pi, right? Okay, and then this z is equal to line between 0 and 2, right, is telling me what the heights are, right? So it's lying between the plane z is equal to 0 and z is equal to 2, right? Okay, so for example, if I change this parameter value here from 2 to probably 4, right, what would happen is that the height of the cylinder would increase to 4, right? Okay, so this z is equal to 0, z line between 0 and 2, right, is in fact what it's doing for me. It's given me, it's cutting off the part of the cylinder that I want, right? That the cylinder lies between your plane z is equal to 0 and z is equal to 2, right? Okay, so the heights come from this condition over here, the z line between 0 and 2. Radius comes from the coefficients, right, of the cos theta and the sin theta, right? Okay, the theta going between 0 and 2 pi means you're going straight around the cylinder, right? And this form, the overall sort of form, cos theta I plus sin theta j plus zk, right, is telling me that the cylinder is centered around the z-axis, right? If I mix this up, for example, if I had 3 cos theta and then I had, say, 3 sin theta k over here, right, and probably I had a yj, right, what that would give me is that would give me a cylinder centered around the y-axis, right? But in this class, really, we're just going to consider cylinders centered around your z-axis, right? Anyway, so this surface S over here, to do my surface integral, I would want a parametric description of S, right? So this is the parametric description of S, right? And now that I have that, right, what I'm going to do is I'm going to use that to calculate the surface integral, right? So working out the surface integral, I need a parametric description, right? Okay, and as I said, I mean, right, so when we're doing the surface integrals, we're going to do it two ways, right? We're going to do it using a parametric description, and then later on what we're going to do is you could actually work it out in a certain special case where your surface S is where your surface S over here you can actually project down to give you a well-defined region in the xy plane, right? So for example, this hemisphere over here, right, when I project it down into the xy plane, I will get a disk, right? Okay, but the point I want to make over here is that this, for us in this class, there's two ways to to work out surface integrals, right? You could work it out using a parametric surface over here, or you could work it out in this situation where you have a surface S over here that's lying on a graph of a function, and then you can project a region R, right? In which case you'd use this formula, right? Okay, so I guess the short story is that for surface integrals, at least for the functions, you're going to have two formula, right? One for parametric surfaces and one for this situation over here, right? Where you're going to have a graph z is equal to g of xy, right? Anyway, so we'll get to this, right? Let's go back to our example. All right. Okay, so we want to work out the surface integral. This is our function over here. We give on your surface S here. And because we're using this formula, which requires a parametric surface, we would need to describe S as a parametric surface, which we talked about already over here, right? Okay, now next thing in this formula, well, you should notice that you're going to have this RU cross RV, right? And it's RU over here, where this U is for your parameter U here. And the RV, this V here, is for this parameter V, right? In this case, the parameters are theta and z, right? So what we're going to do is we're going to construct r theta and rz, right? And that is just because we're calling the parameters theta and z over here instead of calling them u and v, right? Okay, so what is r theta, right? Well, r theta is, to get that, what you're doing is you're differentiating each of these component functions with respect to theta, right? And when you do that, you're going to get minus 3 sine theta here, right? Which is just minus 3 sine theta. Differentiate the 3 sine theta here, right? You're going to get 3 cos theta. When you differentiate z with respect to theta, right, you get 0, right? So the r theta is minus 3 sine theta I, 3 cos theta j, and then 0k, right? And then you'd also need rz, right? Because what you'd want to do is form this cross product r theta cross rz, right? Okay, so the rz, what you're going to do is differentiate again, right? But now you differentiate in the component functions with respect to z, right? So this will give me 0 here. This will give me 0 here. And I will get a 1 over here, right? Okay, so what I have is 0 here, 0 here, and I'm going to have a 1 over here, right? Right, and now that I have the r theta and the rz, right, I'd need to take the cross product of r theta and rz. Notice you want to do it in this order here, right? This is your first parameter and this is your second parameter, right? So you'd have r theta, rz. So you'd want to take the cross product of r theta and rz, right? You don't want rz cross r theta because that would in fact throw off everything by a minus sign, right? Anyway, so I have r theta cross rz, right? And I want to take this cross product, right? And you do your cross product in your normal way, right? You work it out via determinant, right? So the vector for the r theta is minus 3 sine theta, 3 cos theta, and 0, right? So you put this vector over here in your second row. And then you put the vector for the rz in the third row over here, 0, 0, 1. And now you work out this determinant here, right? So this determinant would be, the I component would be 3 cos theta times 1 minus 0, which is 3 cos theta. Okay, and then the j component, right, would be this minus 3 sine theta times 1, right, minus 0, which is minus 3 sine theta. But for j, you're going to have an associated minus. So you have minus 3 sine theta, which is 3 sine theta. And then for the k, when you work out this 2 by 2 determinant, it's going to be 0 times the 3 minus 3 sine theta, which is 0, minus 0 times 3 sine theta, which is also 0, right? So you're going to get 0 minus 0, which is just 0. So 0k, and I didn't bother to write it in because 0k is just 0, right? Okay, so the r theta cross rz is 3 cos theta I plus 3 sine theta j, right? Now the nice thing is, if you have a cylinder of this sort of form, right, where it's 3 cos theta I and 3 sine theta j and zk, right? So in other words, a cylinder that's centered around your z-axis. The r theta cross rz would always work out to be this form, right? Notice this 3 cos theta I and 3 sine theta j is really this over here, right? The 3 cos theta I plus 3 sine theta j, right? So it's a nice way to check your working when you working out the r theta cross rz for a cylinder, right? This is really only if you have a cylinder, say, centered around your z-axis, right? Okay, it's going to be different if you have different parametric surfaces. Anyway, so I have this r theta cross rz, right? And notice in this formula, what I'd need to do is I'd need to take the modulus of that. Okay, so the modulus of that is the length of this vector, right? R theta cross rz is a vector, right? Well, more precisely, it's a vector field. But anyway, so you take an modulus of the vector, right? And the modulus of the vector is you square your components, right? So you're going to get 3 cos theta squared, which would be 9 cos squared theta, 3 sine theta squared, which would be 9 sine squared theta. You could factor out the 9 over here, so you're going to get 9 times cos squared plus sine squared, which is 9 times 1. So this is square root of 9, and the square root of 9 is equal to 3, right? Okay, and I guess the next good thing about doing this, if your parametric surface is a cylinder centered around the z-axis, right, then the modulus of r theta cross rz, right, is in fact just going to be equal to the radius, right? So the radius is 3 over here for a cylinder, right? So r theta cross rz, the modulus of it just works out to be 3, right? Okay, right, so now I have all my information to actually start working out the surface integral, right? The hard part is working out this expression, the cross product here, right? And in this case, it's the r theta cross rz, right? Okay, so this is, I'm using now the definition of the surface integral, right? And what this is saying, in order to work out the surface integral, I'm going to integrate it over your parameter space, right? And the parameter space is this given to me, is this over here, right? Where this parameter space is coming from, we talked about is the theta has to go between 0 to 2 pi to go straight around the cylinder. Right, the theta has to go between 0 to 2 pi to go right around the cylinder, and the z has to go between 0 to 2 to get your height from z is equal to 0 to z is equal to 2, right? Okay. Right. So, and as I said, right, how you work out your surface integral is you work out your surface integral over S by pulling back the information by integrating everything over a region R in a plane, right? Okay, so that is what's going on over here, right? At this point, your surface integral, you're going to work it out by integrating over a region R in the plane, right? And the region R in the plane over here is this region, right? So your parameters are theta and z, right? So what you're considering is your parameter space theta and z, right? Or plane, z theta plane here, right? Your region R as specified. Okay, so the region R that's specified over here is in fact a rectangular region, right? You see in that the theta lies between 0 and 2 pi, and the z lies between 0 and 2, right? So this is a rectangular region, right? So when you have your surface integral, and so your surface integral over this surface S over here is going to turn out to be a double integral over this region in the theta z plane, in a plane, right? So this is now, you go from a surface integral to a double integral, right? And the next thing is, well, what you're doing is you're using your information from your parametric surface, right? So what's your information from your parametric surface? Wherever you see the x over here, you're going to replace by the components from your parametric surface. So from your parametric surface, the x is equal to 3 cos theta, the y is equal to 3 sine theta, the z is equal to z, right? So where you see the x, the y, and the z, right, you replace by the corresponding functions of theta and z, right? So that is what this is saying over here, right? Where you see the x, the y, and the z, you replace by the corresponding functions from in your parametric surface, right? So here where I see the x, the y, and the z are replaced by the corresponding functions of the parametric surface. So I replace the x by 3 cos theta. I replace the y by 3 sine theta, right? And the z is actually just equal to z, so the z just replaces itself, right? So I have z, right? So notice I have 3 cos theta squared, y 3 sine theta, and then z squared, right? So that is what this is saying over here, right? This is saying that surface integral is the integral over this parametric surface here that's floating in three-dimensional space, right, is actually equal to a double integral in the plane, right? And how you do it is you replace where you see the x, the y, and the z over here, you replace it by the components from your parametric surface, right? Okay, so that is what this is saying. And then finally, you need to multiply by this factor r theta cross rz, right? Which is a scaling factor, right? Because when you pull back your information from here to here, right, you want to notice that this surface S over here, you may not actually see it here, right, but this surface S here is the areas over here actually stretched out as compared to this region R by a factor of 3, right? So that is what the R theta cross RZ is doing for you, right? It's a scaling factor between these two areas over here, right? Okay, right? But anyway, take it for the point of view of working out the calculation. I need the R theta cross RZ, and we work that out. It's 3, right? Okay, so surface integral turns out to be a double integral, and this is now just a double integral over a rectangular region, right? And while it might seem sort of complicated and so on, right, this is just, you just integrate in with respect to theta and z. So this is in fact the easiest form of a double integral, right? Where you're integrating over a rectangular region, right? Okay, so I'm integrating this function over here over this rectangular region, right? And how you're going to do that, right? Well, over here I had a 3 and I pulled the 3 outside, right? So I pulled this 3 from the modulus of the r theta cross rz. I pulled that outside, right? Because it's just a constant, right? I expanded this out, so I'm going to have a 9 over here times this 3, which would give me the 27, and I have a cos squared times the sine, right? And then plus the z squared, right? So I'm integrating this function over here of theta and z, right, with respect to theta and z, right? And it's a rectangular region, right? So if it's rectangular, you could integrate with respect to y then x, right? And what's corresponding to y over here is your z-axis, and what's corresponding to x over here is your theta axis, right? So integrate with respect to z then theta, right? Now, if you're doing this, you want to make sure that you have your limits correct, right? Okay, and the limits come from the region R, right? Remember, what you're doing is you're integrating over this region here, right? Okay, so for the z, right, notice the z is going between 0 and 2, right? So that's, if I'm integrating here with respect to z, integrate between 0 and 2 for the z, and then this outside integral with respect to theta, right? What I need are theta values, which are going between 0 and 2 pi, right? Or you could read it from your set description for R, right? This is R over here. And your set description for R is that the Z goes between 0 and 2, right? So for the Z over here, the Z is going between 0 and 2. The theta is going between 0 and 2 pi, right? 0 and 2 pi over here, right? Okay, and then now you do your integrals, right? So you integrate the inside over here. You integrate with respect to Z, right? This cos squared sine theta times 27, right? This is a constant as far as z is concerned, right? So you're just going to get the constant times z, right? So that's how you get the 27 cos squared theta sine theta times z over here, right? And I'm integrating with respect to z. So when I integrate the z squared with respect to z, I'm going to get z cubed on 3, right? And then what you do is you put in z values here. So you put in z is equal to 2 and z is equal to 0, right? Putting in z is equal to 0 will just give me 0 here and 0 here. So the only thing non-zero that I will get is when I put in z is equal to 2, right? So I'm going to get 2 times 27, which is 54, and then 2 cubed, which is 8. So I get 813, right? And then what I do now is I integrate this with respect to theta, right? So integrating the 8 on 3 with respect to theta is not hard, right? This will just give me 8 theta on 3, right? To integrate this here, right, you could use a substitution. U is equal to cos theta, right? Or you just integrate the cos squared, right? And when you integrate the cos squared, you're going to get cos cubed on 3, right? But you want to make sure that whatever this is, when you differentiate it, you get back what you have over here, right? And if I differentiate over here, I differentiate the cos cubed, right? The 3 would come down to cancel with this 3 to give me a cos squared. But then I need to multiply by a minus sine theta, right? So that is, because I need to multiply it by minus sine theta, that is what introduces this minus sign in this answer here, right? Or if you want, you just use your substitution, u is equal to cos theta, right? Anyway, so once I do this integral with respect to theta, this is what I get, and then I put in the values. Theta is equal to 2 pi and 0, right? Now the thing is, when I put in 2 pi in for cos cubed, right, and I put in 0 in for cos cubed, I will actually get the same answer, right? So putting in the 2 pi and putting in the 0, right, remember what you're doing is subtracting these. So if I have just a normal trig function, right, and I don't have any sort of multiple, this is not cos cubed of 5 theta or theta on 4 or anything like that, right? Well, it would actually work for 5 theta, but it's not fractional theta on, say, 4 or theta on 2, right? If I put in the 2 pi and in the 0, these would just cancel off to give me 0, right? So the only thing I need to work out over here is when I put in the 2 pi and I put in the 0, right? When I put in the 2 pi, I'm going to get 8 times 2 pi, which is 16 pi, and the 3 will cancel with this 3 to give me my answer, which is 16 pi. Right, so let's recall what I said, that if I have a surface integral, right, and the function defined on the surface itself, right, so on your green surface, for example, over here, right, if the function is equal to 1 at each point on your surface, right, and you do a surface integral of 1 over your surface, right, then what you end up getting is you end up getting the surface area of S, right? Okay, so let's actually do a calculation involving this, right? So we want to look at this example. Okay, so I have a truncated plane with this parametric description, and that is, we saw this already, right? Here the y is equal to 1, right? So the y component is equal to 1. The x component is equal to u, and the u lies between 0 and 1, which means that the x is going to lie between 0 and 1. The z is equal to v, and the v lies between 0 and 1, so the z lies between 0 and 1, right? So this is your truncated plane over here. So this here is y is equal to 1, right? So your plane there is y is equal to 1, right? And the two other conditions tell you that the x right, the x must lie between 0 and 1, and the z must lie between 0 and 1, right? Okay, so I have this truncated plane, and what I want to do is I want to find the surface area of it, right? Now this here, I don't need a surface integral to do this, right? Because this is just a square here, right? Okay, so the square, each side is of length 1, right? So the area of the surface area here would just be the area of the square, which is just 1 times 1, which is 1, right? Okay, but let's go through the surface area calculation and see that we get the same answer, right? Okay, so I want to get surface area of this truncated plane, right? And as I said, you can get surface area by evaluating a surface integral where your function inside your surface integral is equal to 1, right? Okay, so this is what we want to do, and well, how are we doing this, right? Well, what we're doing is we're calculating a surface integral. Okay, so if we calculate a surface integral, we need to use this formula here, right? This truncated plane is given to us as a parametric surface, right? So we're going to be using definition of a surface integral as when the S is given as a parametric surface, right? Okay, so what I would need is, first of all, is I would need the RU and the RV, and I need the cross product of that, right? Okay, so this is the R here, right? To get the RU, what you're going to do is you differentiate each of these components here with respect to U, right? And when I do that, when I differentiate U with respect to U, I'm going to get a 1 here. I'll get a 0 here, and I get a 0 here, right? So RU is just going to turn out to be equal to I, right? Okay, so RU, what you're doing is you're differentiating the components with respect to U, and you just end up with a 1, differentiate the U over here with respect to U to get 1. You get 0 here and you get 0 there, right? So I get I over here, 0J and 0K. So the RU is just I, right? And I would also need RV, right? And to get the RV, you differentiate with respect to V, right? You differentiate in your component functions with respect to V. So differentiate U with respect to V, you're going to get 0 here. Differentiate this 1 here with respect to V, you're going to get 0 here. And differentiate the V with respect to V, you will get 1 here, right? So you're going to get 0 here, 0 here, and then you're going to get a K there, right? Okay, so 0, 0, and then a K here, right? Right, and what I would need is RU cross RV when I'm working out this surface integral, So the RU cross RV is I cross K, and you can check that I cross K is equal to minus J, right? And really, for surface integral of a function, what I need is the modulus of the vector RU cross RV. So I need modulus of the vector J, so the length of this vector J. Now this J is a unit vector, which is of length 1, right? So the modulus of it is 1, right? So RU cross RV is going to be equal to 1, right? Okay, so right, now I use my formula for surface integral. I want surface area, so what I'm doing here is I'm integrating 1, right? So the function, the small f in this case, is just equal to 1, right? Now, in this general formula, right, what you're supposed to do is wherever you see the x, y, and z, right, you replace by the corresponding component functions, right? But for this over here, the f is equal to 1, right? So there's nothing to replace, right? There's no x, y, or z to replace, right? So you're just going to get, if this is 1 over here, you'll have 1 over here, right? But you still have this RU cross RV, the modulus of it over here, right? And that we worked out to also be equal to 1, right? So here, this is a surface integral, right? And here, what you're doing is, this is working out the double integral. And inside here, it's also equal to 1, right? Okay, so remember what you're doing when you go in from your surface integral, right? So when you have your surface integral, you're integrating over this surface S over here, right? And how you actually do it is you're pulling back all your information onto your region R here, right? So in this example, right, the S is this green truncated plane over here, and the R is this pinkish region, square region in the plane, right? Okay, in the UV plane. Right, so to work out this surface integral, right, so to work out this surface integral where you integrate in 1, right, so to get the surface area, you're working out, that turns out to be equal to a double integral, and the double integral here, it's just 1 on the inside over here, right? So I'm integrating 1 over here over a rectangular region. Okay, so your region R, your rectangular region, and that's specified for you, right? In the description of your parametric surface, the R is given saying that the U lies between 0 and 1, and the V lies between 0 and 1, right? So this R over here is the same R that I'm talking about over here, right? So this is R also, right? It's just a different diagram for it, right? Okay, so it's the same R over here, and so my surface integral turns out to be equal to double integral of 1 over this square region, right? Now this is square, is rectangular, right? Okay, so to do this, you can integrate with respect v then u, or u then v, right? And this working over here, what I did is I integrate with respect to u first, then with respect to v, right? If you integrate in with respect to u, right, what you need is limits for the u, right? And the limits for the u, you see over here as 0 and 1, right? Or you could see that also from a set description that the u lies between 0 and 1, right? So the limits for the integration with respect to u between 0 and 1, right? And the limits of integration for the v, which is the outside integral over here, is also 0 and 1, right? Or you could see from here, you integrate in between 0 and 1 here, right? Okay, and now this is just a normal double integral, iterated integral. Integrate with respect to u first. Integrate 1 with respect to u, you're going to get u, right? Put in your u values 1 and 0, which would just give me 1 over here, right? Okay, so this double integral over here would simplify down to a single integral of 1 over here with respect to v. And here, when you integrate 1 with respect to v, you're going to get v, and you put in 1 and 0, you're going to get 1 minus 0, which is just this 1 over here, right? Okay, so when I work out my surface integral, right, the surface integral, according to the formula, for working out a surface integral for a parametric surface, right? The surface integral of 1 over here, which is just giving me surface area, right, is equal to a double integral, right? And when I work out all of this here for this particular situation, this turned out to be equal to 1, right? So this surface integral of 1 turned out to be equal to a double integral of 1. And here I just work out the double integral over a rectangular region in a normal way, right? And this here, right, remember I said that integral of 1, surface integral of 1 is surface area of S. So what this is this integral of 1 with surface integral of 1 over the surface S is the surface area of this truncated plane, and it turned out to be equal to 1, which is what we expect because this is just a square located in three-dimensional space, a square of side length 1, right? So the area of the square is 1, and that agrees with our answer over here. Okay, so let's go back to the parametric surface that I was talking about in the beginning of this lecture, right? So I have this parametric surface, which is a truncated plane, right? So parametric surface over here, where the u and v lie between 0 and 1, and the v lies between 0 and 1, right? So region R is this pinkish region over here in the UV plane, right? And the parametric surface is this truncated plane, right, in the XY in three-dimensional space, okay? Right, and what I was talking about for this example is that I'm regarding this as, say, a sheet of metal here, and that the area density is changing, right, according to this function, right? So when down here on your bottom edge, z is equal to 0, area density is going to be equal to 1 plus 0 over here. So the area density is 1 over here, right? And on this top edge over here, right, where the z is equal to 1, right? Okay, so your top edge, where top edge here, the z is equal to 1. And on that top edge, the area density, according to this, you put z is equal to 1 into it, it is 3, right? Okay, so this has variable area density, right? And for this particular function, right, because the area density is variable in a linear fashion, right, and it's increasing from 1 to 3 over the 1 on the bottom edge, 3 on the top edge in a linear fashion, right? This particular sort of relatively simple area density function, what I could do is I can find the average area density, which I have 1 over here on this bottom edge, 3 over here on this top edge, and it's increasing linearly from 1 to 3, right? So the average area density here is 2, right? Okay, so the mass of this metal plate, this thin metal plate, you can regard as just the average area density, which is 1 plus 3 divided by 2, which is 2, right? Multiply it against the area, right? And this area is, this is just a square over here with side length 1, so the area is 1, right? So the mass of this would be average area density times area, which is 2 times 1, which is 2, right? Okay, so that is working it out by looking at this sort of particular area density function, right? But what I said also is that I can calculate the mass of this metal plate, right, by using a surface integral, right? Okay, so the mass of this metal plate S over here, right, is surface integral of your area density function, right? And the area density function is this area density function here. Right, this area density function over here, right? Over your surface S, right? Okay, so we want to integrate, in order to get the mass, we want to integrate this area density function over your parametric surface S, right? And how we do this is we use the fact that S is a parametric surface, right? And we use what we used before to calculate the surface integral of a parametric surface, which is this formula here, right? Alright, okay, so the parametric description that I have, right? Notice over here I need to work out the RU, the RV, I need to take the cross product and so on, right? Okay, so the parametric surface that I have is this parametric surface here, right? Now, we actually saw that parametric surface already, right? Which was this one here, right? No, it's the same parametric surface, right? The RUV is UI plus J plus VK. The parameter values lie between 0 and 1, right? And it's the same truncated plane, right? The difference between what I have here is here what I was doing is I was integrating 1, right, over this parametric surface. And now what I'm going to be doing is I'm going to be integrating this area density function, right, which is different from 1, right? Okay, so I'm going to be integrating this area density function over here, right? But between these two examples, right, the parametric surface is actually the same, right? Okay, so your parametric surface is the same, right? So it's the same parametric surface that I'm integrating over, which means that the RU and the RV are in fact going to be the same, right? So the RU, notice over here when I calculate the RU, right? RU means I'm differentiating your component functions with respect to U, right? So I'll have a 1 here, I'll have a 0 here, and I'll have a 0 here, right? So I get the RU is equal to I. And similarly, when I work out the RV, I'm going to get K over here, right? So for this parametric surface, the RU cross RV would be I cross K, right? Which is minus J, right? And the RU cross RV, the modulus of that would be work out to 1, right? Okay, so all of these things, the RU and the RV and the cross product of the RU and the RV, right? Those have to do with the parametric surface that was given to you, right? And in this example and in this example, it's the same parametric surface, right? Okay. All right, so we want to work it out, right? So I'm going to work out my surface integral, right? And here I'm using my formula for the surface integral. My parametric surface is, sorry, the area density function is 1 plus 2z, right? So what I'm supposed to do is in this function over here, wherever I see the x, the y, and the z, right, I replace by the corresponding functions, right? and the corresponding functions, x is equal to u, y is equal to 1, and z is equal to v, right? So when the row A is equal to 1 plus 2z, right, what I do is replace the z by the v. So instead of 1 plus 2z, I'm going to have 1 plus 2v, right? And then the ru cross rv, right? As I said, it's the same parametric surface S as this one over here. So the ru cross rv, the magnitude of it is also equal to 1, right? Okay, so the area density, integrating the area density over S is going to be the same as working out a double integral over region R, and it's the same region R because remember it's the same parametric surface, right? Alright, so I'm integrating over this region R, and this region R is a rectangular region, right? So in this case, what I'm doing for this example is I'm integrating 1 plus 2v, right, over region R, right? And limits of integration come from the fact that this region R is a rectangular region. Okay, so the v limits are between 0 and 1, which are 0 and 1 over here. And the u limits are between 0 and 1, right, which is 0 and 1 over here, right? So I integrate this, right, and I integrate the 1, I'll get v, right? So working from the inside out, right? Okay, so when I do the inside integral over here, I'm going to get inside integral with respect to v. I'm going to get v over here, integrate 1 to get v, and integrate the 2v to give you v squared, right? And you put in your v values 1 and 0, and when you do that, you're going to get 1 here plus 1 here, which is 2. And that gives you this 2 over here, right? Okay, so this double integral here simplifies down to just an integral of a single variable, and when you integrate this 2, you're going to, with respect to u, you get 2u. You put in your values 0 and 1, and this just gives you 2, right? Okay, so the mass of S for this variable area density, I can get by working out a surface integral over S, right? So to get the mass of this metal plate, when I have variable area density 1 plus 2z, right? Okay, so area density is varying along this surface S over here. To work out this mass, I can work it out via a surface integral, right? So surface area integral of the area density over the surface S. In this case, the area density was given to me as 1 plus 2z. And when I integrate that area density over my parametric surface S by pulling back everything onto this region R, I end up getting 2, right? Okay, so the mass of this metal plate over here is going to be 2, right? And that actually agrees with the method that I used by the previous way I worked it out by getting average area density and multiplying by area, right? For that, when I worked it out that way, I got 2, right? And when I worked it out using a surface integral, right, of the area density over S, right, I also got 2. Alright, so we saw how to work out surface integral of a function over a parametric surface, right? And we saw 2 examples where we did that, right? So we integrated over this parametric surface over here, which was a cylinder centered around the z-axis. And the parametric description was given over here, right? The r theta z was 3 cos theta I plus 3 sin theta j plus zk, right? Okay. And then we also looked at this example over here where I was evaluating a surface integral, right, over this parametric surface, which is a truncated plane, right? Okay, so this truncated plane is a parametric surface, right? This cylinder here centered around your z-axis was a parametric surface, and we worked out a surface integral for those over those parametric surfaces, right? Now what we want to do is we want to consider a surface integral formula where it's not for a parametric surface, right? This formula actually comes from using this, right? By actually obtaining a suitable parametric description from S here, right? But the formula is set up so that you don't actually see the parametric description for S, right? And in a sense, this is somewhat easier because this formula, the formula here, when you're working it out for a parametric surface, takes a certain amount of work because you'd need to work out the RU, the RV, you'd need to get your cross product, right? And then take the magnitude of it and so on, right? Okay, so you have this term here that you would need to work out, right? And in this second formula here, this term, the RU cross RV, all of it is in fact worked out over here as the square root, right? Okay, so in a sense, it's somewhat less work, right? Right, so what's the setup for this, right? Okay, so the setup for this is what I have is I have a surface S over. Okay, so I have several things going on here, right? What I have is the graph of a function, which is z is equal to g of xy, right? Now you want to remember that the graph of a function is going to form a surface for me in three-dimensional space, right? So z is equal to g of xy is this light gray surface over here that's in three-dimensional space, right? Okay, and the surface S that I'm going to be integrating over is in fact going to be a subset of that, right? Okay, so the surface S that I'm going to be integrating over, it would be this dark gray uh, subset of the graph, right? So it's not the entire graph, it's only piece of the graph, right? The dark gray part over here, right? Okay, so this formula here is this formula that I'm going to use, I'm going to talk about is set up for it's for these sorts of situations, right? So in order for you to use this formula, you'd need to have the graph of a function, right? So you'd need to have this g of xy, right? And then you'd also need to have the surface S, right? Okay, so the surface S would be a subset of this graph, so a piece of this graph here, right? And once you have the S here, what you'd need to do is you need to project this S down onto the xy plane to get a region R, which is a R. This region R is on the xy plane, right? Okay, so once you have those three things, right, basically you'd need the g of xy, right? You'd need the surface S that is living on the graph of the graph of z is equal to g of xy, right? And then from that surface S, you project down onto the xy plane to get a region R, right? Once you have those three things, then you can use this formula, right? Okay, so what you want is surface integral of some function, right? It's a function small f over the surface S, right? And the surface S is this dark gray surface S over here, right? Right, so to evaluate your surface integral of your function small f over this dark gray surface S over here, what you're going to do is you're going to work it out as a double integral over the region R, right? And remember this region R you get by projecting the S onto the xy plane, right? And what you do is you take the Z over here and you replace the Z by this G of xy, right? Okay, and then you'd be multiplying by this square root term over here. And in the square root term, that's 1 plus the g of xy, but differentiated with respect to x. So you take this g, take the derivative with respect to x and square it. And similarly, you take the g, take the derivative with respect to y and square it, right? And you form the sum 1 plus dg dx squared plus dg dy squared, right? And then you take the square root of that, right? Okay, so the surface integral over the S here, right, of this function small f is equal to the double integral over this region R down here in the xy plane, right, where you replace the z by g of xy, and then you have the scaling factor, which is the square root of 1 plus dg dx squared plus dg dy squared, right? Okay, all right, so let's see an example of using this here, right? Right. Okay, so I wanna to work this out. What I'm going to do is I'm going to use this formula with the g of xy, right? Alright, so I have a hemisphere, right? And it's a hemisphere of radius a, right? So, well, what is a hemisphere, right? A hemisphere is half of a sphere, right? And we're looking at the top half of the sphere, and it's this mesh part of the sphere, right? It's not this sort of circular gray, dark gray region down there in the xy plane. The hemisphere is really this uh, the gridded looking part, right, which is half of the sphere, right? All right, so this is the equation of your hemisphere, right? The equation of the hemisphere is z is equal to this function of xy, right? And this is of your form z is equal to g of xy, right? Okay, so the z is equal to g of xy. The g of xy in this case is actually this function here, right? The square root of a squared minus x squared plus y squared, right? And you could always check and see if you square this both sides over here, you're going to get z squared over here, and you get a squared minus x squared plus y squared. And if you carry the x squared plus y squared across on this side, what you'd have is x squared plus y squared plus z squared is equal to a squared, which would be a sphere of radius a, right? But what I have is half of that, right? And half of that is z is equal to square root of a squared minus x squared plus y squared, right? Okay, so the g of xy, right, the graph of the function, right, is in fact that corresponds in this picture to this dark gray area here, right? So this is the graph, right? Right. In this particular case, for this z is equal to g of xy, right? This dark gray, the dark gray and the light gray are going to be the same thing, right? So it's as if you expanded this dark gray over here to cover this entire light gray thing over here, right? Anyway, so this is z is equal to g of xy, right? And right, so in this formula, what I need is the g of xy, and that's given to me over here, the square root of a squared minus x squared plus y squared, right? And what I'd also need is the region R in the xy plane, right? And to get the region R in the xy plane, what you need to do is you need to look from the top over here, and you take a plan view, right? So you look down, uh, in the reverse direction of your z-axis, and when you look down, right, what you would see is you would see a circular disc, right? So when you look, okay, so if you project down, right, and if you consider that this hemisphere over here, say it was some dark color and so, right, when you look down, right, you look down in the opposite direction for your z-axis, so you're looking along your z-axis and you're looking down, right, what you'd see is you'd see this a disk over here of radius a, right? And in this diagram here, this is the region R over here, which is this disk of radius a, right? So the R over here is this dark gray region here, which is the same as this R over here, right? Okay, so if you're comparing this general picture to what I have, right, the S is the gridded half hemisphere over here, right? And the region R, that when you project this S onto the XY plane, the region R is this disk down here in this dark gray disk in the XY plane, right? And it seems sort of elliptical over here, but if you looked in a plan view, right, what you would get is you'd see an actual disk, right, in the XY plane, right? So the region R is a disk in my XY plane, right? Okay, so for this problem, right, the g of xy is the square root of a squared minus x squared plus y squared, right? Your region R is the disk down here in the xy plane, which is this disk over here. Right. Okay, but what's the function f, right? What am I integrating, right? Well, what they want me to do is find the surface area of this surface capital S over here, right? And you want to remember that finding surface area is integrating 1, right? So the surface area of S is equal to the integral of 1 ds, right? This is a typo over here. You're just supposed to have just one S here, right? Okay, so this is what I want to work out, right? I want to work out surface integral over the surface S over here of the function 1, right? So in this case, so for this general formula over here, the function is equal to 1, right? Now, what this formula means is everywhere you see x, y, and z, right? Well, you'll keep the y, you'll keep the x, right? But you'll replace the z by g of x, y, right? But over in this particular case, right? Okay, so here what it means is where you see the x, y, and z, you replace by x, y, and g of x, y respectively, right? But in this particular case, I have no x, y, or z, right? So there's nothing to replace. This f over here, small f, is 1, right? So over here, I'll get a 1 over here, which is just a 1 over here, right? So all I'm left with is the square root sign, right? And the square root sign with the 1 plus dg dx squared and the dg dy squared, right? Okay, right? So this is what this formula here is coming. This given to get the surface integral of 1 over the surface S, right? As a double integral over R, what I'm doing is I'm using this formula where the small f is equal to 1, right? So when the small f is equal to 1, I have a 1 over here, and the 1, it's 1 times the square root, which is just the square root sign itself, right? Okay, so I have this, and I need to work this out, right? Now the next thing that I would need is the dg dx and the dg dy, right? Okay, so the g of xy, the z is equal to g of xy, right? G of xy is this what's given to me, right? So this z is equal to g of xy. This graph over here, in fact, gives me the hemisphere, right? So the g of xy is the square root of a squared minus x squared plus y squared, right? And what I need to do is I need to work out the dg dx and the dg dy, right? Okay, so you need to differentiate the g with respect to x, right? And when you differentiate the g with respect to x, right, what you will get is this expression over here, right? So this would be the dg dx over here, right? Although there's a mistake, right? This is supposed to be minus, right? It doesn't affect the answer in this case because if it's minus over here and once you square, right, the minus sign will go away, right? But anyway, so when I take this g of xy and I differentiate it with respect to x, right, what I'm going to get is I'm going to get this expression over here, right? When I take the g and I differentiate it with respect to y, what I'm going to get is I'm going to get this expression over here, right? Well, it's supposed to be a minus there, right? Okay, so in both cases here, I'm supposed to have a minus over here and a minus over here, right? Anyway, so I have this somewhat complicated expression that I need to integrate with respect to r, right? And what you do is you start simplifying, right? So I need to square everything over here. When I had the minus over here, this minus would go away when I square, so I'd have an x squared here. And then I'm going to square the square root sign, right? So I'll have a squared minus x squared plus y squared on the bottom, right? So I have x squared on a squared minus x squared plus y squared. And likewise over here, I'd have y squared on a squared minus x squared, right? And what I have is a common denominator for both of those, right? And then when I add, I'm going to get x squared plus y squared on top, right? Okay, so something like this when you're doing, you're using this sort of formula over here with the dg dx and the dg dy, right? This happens quite a bit, right? So you will need to do some simplification because integrating with a square root sign is never really very easy, right? So somehow you'd want to get this inside over here to simplify, right? Okay, so that is what I was doing over here, right? And so far I have this, right? Now what you want to notice is this is just 1 over here and this is a fraction, right? So what you do is you take a common denominator here. And when you take a common denominator over here, you're going to have a squared minus x squared plus y squared plus x squared plus y squared, right? So the minus x squared plus y squared will cancel with the x squared plus y squared. And I'm left with a squared over here, right? Right, and what I can do is now I can take the square root here, right? So when I take the square root of the a squared, I'm going to get an a on top, right? And that's actually, I pull that out over here, right? And then I'm going to have 1 over square root of a squared minus x squared plus y squared, right? Okay, and 1 over square root is this expression to the minus a half, right? Okay, so I come down to this here where I'm integrating this expression, a squared minus x squared plus y squared, to the minus a half with this small a out in front, right? And remember that small a is the radius, right? Right, now this is a double integral over region R, right? And the region R that you're integrating over is when you projected this S over here. So project the S to get the region R, which is the dark gray disk down there, which more precisely in a better picture is this disk over here of radius A, right? Okay, so what you want to do is you want to do a double integral over this region R here, right? And in this case, what you need to do is you need to use polar coordinates, right? Because, well, for double integral, the types of regions that we considered would be rectangular, and this clearly is not rectangular. Type 1 or type 2, right? Now this actually you can do in terms of type 1 and type 2, right? But it's easier to use polar coordinates in this case, which is what we will do, right? Okay, so first thing you'd want to do over here is you'd want to express this region over here as a polar rectangle, right? And we talked about this, right? So as a polar rectangle, the small r okay, so when I have a disk, right, I can express the disk as a polar rectangle, and we saw this example already where the theta is going to go between 0 and 2 pi, right? And this value over here is my outside radius, right? So in this case, the outside radius is a, right? So what I would have is I'd have a small a over here, right? Okay, so, and then when I do the conversion to polar coordinates, right? And the conversion to polar coordinates, let's remember that your conversion to polar coordinates is via this formula here, right? Okay, so where you see to convert to polar coordinates, where you see the x and the y, right, you're going to replace the x by r cos theta and the y by r sine theta, right? So this is the conversion from xy to polar coordinates, and that's what I'm using to go from here to here, right? The surface area, which is the integral of 1 ds simplified down to this here, right? And what I'm doing now is, so surface area, which is the integral of 1 ds, was equal to this. So now I'm working out this here, right? And I'm working it out by a conversion to polar coordinates. So the x is going to turn into r cos theta, the y is going to turn into r sine theta, right? I have r dr d theta, which is this r dr d theta, right? And the limits of integration come from the expression of this disk over here as a polar rectangle, right? Okay, and as I was talking about over here, right, when you have a disk like this, right, the theta is going to go between 0 and 2 pi, right? Okay, so the limits of integration for this theta would be 0 to 2 pi. And the limits of integration for the r would be from 0 to the outside radius, and the outside radius here is a, so it's 0 to a, right? So this is how I get the conversion from the xy to polar, right? And now this over here is just normal iterated integral, right? you want to simplify here a little bit, what you could do is you could pull out the r squared and you'd have cos squared plus sine squared. So what you'd get is just an r squared over here, right? Okay, so here I have a squared minus r squared, and that is to the power minus a half, right? Okay, and I have an r outside over here from the r d theta, right? Okay, so how you would integrate this is you'd substitute u is equal to a squared minus r squared over here, right? That's one way to do it, or what you want to realize is you're integrating this bracket, which is to the power minus a half, right? So when you integrate the bracket, you're going to get minus a half plus 1, which is plus a half, right? And you want to make sure that the rest of it is correct, right? So when you differentiate over here, you get back what you have over here, right? Okay, so when I differentiate this a squared minus r squared to the half, right, this will turn to a minus a half. I'd have a minus 2r over here, which would hit this minus sign to give me a 2r. And then the half that came down in front, I'd have a half times the 2r, which would give me the r, right? Okay, so when I differentiate this, I will get this over here, right? So either you can look at it and just work it out mentally, right? And just adjust the minus signs and the constants appropriately. Or you could use a substitution, u is equal to a squared minus r squared, right? Anyway, so what you do is you integrate over here with respect to r first, right? When you integrate with respect to r, you get this minus a squared minus r squared to the half, right? And then you put in, want to do this inside integral, you do your integral with respect to r, and then you put in your r values. R is equal to a and r is equal to 0. Putting in r is equal to a gives me a squared minus a squared, which is 0, right? So putting in r is equal to a would give me 0. Putting in r is equal to 0, right, gives me a squared to the half, which is a, right? And I'm subtracting that, so I'd have minus minus a, which is plus a, right? Okay, I have this outside a over here, right? Anyway, so I integrate this a. What I'd get is, when I integrate the a with respect to theta, I'd have a theta, right? And then I put in the 2 pi and the 0, right? Which would give me 2 pi a, right? So this integral here would be 2 pi a. And then I have, I need to multiply it by the a on the outside here, which would give me 2 pi a squared, right? So the surface area of S is 2 pi a squared, right? And let's recall that if I have a sphere, right, a sphere of radius r, right, then the surface area of a sphere of radius r is 4 pi r squared, right? And here I'm calling the radius a, right? So if this was a sphere of radius small a, then the surface area would be 2 pi a squared, right? But you want to notice over here I have, okay, so here the surface area of the entire sphere is 4 pi a squared, right? But over here what I have is 2 pi a squared, right? But remember what I was doing, right? What I was doing is I was calculating surface area of just this top hemisphere over here, right? So the surface area that I'm calculating is in fact going to be half of the surface area of the entire sphere, right? And half of the 4 pi a squared would be this 2 pi a squared, which I get as an answer.